So, thank you everybody for coming tonight. My name is Burka. I'm a member of the 2 Sigma Labs team, and I have a great interest in software engineering. I want to understand how we build software. I want to know how to do it better, and I'm particularly interested in using automation to do that better. One of the areas I'm really interested in is technical debt. So technical debt is the long-term cost that we incur for short-term goals. There are always changes that we know we should make to our code bases, but we put off because we have more urgent things that have to be done. But if we don't eventually deal with this technical debt, it incurs interest, and we have to pay that interest off in increased development costs down the road. And it makes it harder for us to add new features. So recently, I've been involved in a project at 2 Sigma that I spearheaded to use automation to help decrease our technical debt. So we actually built a framework of tools that let us run automated processes on all of our code and apply refactorings to them, test them, submit them for code review, and then push them into the system. So that's one of the reasons that I really love this paper. So, why do I love this paper? On first reading, you might not see anything really groundbreaking here. But I kept coming back to the paper. There were some things in it that really got me. The authors are demonstrating a practical solution to a practical problem. And I really like the way that they test and evaluate their solution. So what is the problem they're solving? It's the question of how can we keep our old code up to date with current best practices? And what's the practical solution? It's refactoring, and completely automated refactoring. So, the reason that they want to make this refactoring is because of Java 8. Java 8 included a group of features that were called Project Lambda during their development phase. Project Lambda is really exciting, and it's probably one of the biggest changes ever to happen to the Java language. One of the chief complaints people have about Java is the verbosity. There's so much boilerplate. You have to repeat the type name to say what the variable is going to be, then you have to say it again when you allocate that variable. When you do an inner class, you have to say the name of the class. You have to say the name of the method you're overriding. You have to add an annotation reminding yourself that you're overriding a method. Then you need like 6 curly braces to close the whole thing off. So lambdas make that far simpler. And it actually continues a trend that's been going for a while. I think Java inherited or was born with this verbosity, and they've been trying to move away from it. In Java 5, we got the enhanced for loop that made it far easier to iterate over collections and arrays. In Java 7, we got the diamond operator, which isn't actually an operator at all, but it's diamond shaped. It's the thing that means that you don't have to say that your hash set of strings is actually a hash set of strings when you allocate it. You can just say, this hash set of strings is a hash set, you figure out what goes in it. So Java 8 lambdas take this way further. They're really just anonymous inner classes that implement a single method. Now, this sounds like a bit of a cheat at first, but it's actually a really powerful way to do it, because Java already had anonymous inner classes. This is just a new syntax for something it already had. So we get lambdas, we get most of the power that you get from lambdas in a functional language, but we can retrofit them into the language. Anywhere where you were already using an anonymous inner class, you can now use a lambda. The syntax just got far simpler. So the other thing that lambdas allow, and one of the main motivating factors for doing this work to add them to the language, is the new stream library in Java 8. The stream library is based on the the operations that you may be used to in functional languages already for dealing with lists. They give you the ability to do things like map and filter and reduce, the things that you're probably used to if you programmed in Clojure or Scala or Haskell, but Java programmers haven't been able to use until now. The compose stream operations that they allow. The compose stream operations that they allow are more semantically explicit than free-form loops. The programmer has to explicitly say, and they encourage the programmer to think about these steps. A chain of well-defined filter, map, reduce operations. Instead of the free-form for loop, you get these well-defined steps. It's easier to understand. But the biggest selling point for the streams library is parallelism. Converting a chain of streams to be parallel.
Just a little closer.
Converting a stream of chains to be parallel is just a one-word change. You don't have to introduce hundreds of lines of thread code to manage it. It just happens for free. So let's look at an example. This is an example of replacing an imperative for loop, Java 7 style, with a stream style functional loop in Java 8. So you can see that we had the for loop here. It iterates over a list of rules and calls some mutating function on them. In the new style, the code looks very, very similar, except we're using a stream and a lambda. So you can see here, instead of curly brackets, we've got round brackets. This is a lambda. It's not a block expression, although you can have curly brackets in your lambdas as well. But we're calling stream to say we want the streaming interface, and then we call for each, which lets us operate on each thing in the list. So this isn't a particularly great motivation. It actually looks like I had to write a little bit more code to do the same thing. But what if we want to parallelize that? This is the Java 7 code to do this in parallel. And I cheated a little bit here. I cut some corners. This isn't the proper way to parallelize it. This is the short way. And this is far better than the way you had to do it in Java 5. So we allocate a thread pool. I have to guess how many threads I'm going to use. I'm going to say 4. If I have 32 CPUs on my machine, well, they'll be idle. Then I have to wait while it terminates. I actually have to do that in a loop. I don't think this will ever not finish, so I'm just going to loop for 1 day and hope it finishes, because there's no other way to do it. And it might throw interrupted exception. Can everyone in the room who knows how to correctly handle interrupted exception in Java raise their hand? Well, a couple people way kind of half-heartedly thinking maybe. Yeah, interrupted exception is a nightmare. Almost nobody knows what to do with it.
Thread death exception.
Deprecated. Thread death, you're not supposed to use that anymore. The scary thing about thread death is it can be thrown from anywhere.
You can also catch it by mistake.
Yeah, that was a bad thing. Yeah, you could stop your thread from dying if you caught it. That was an immortal thread. There's a reason they deprecated it. Okay, so this was the Java 7 way. Here's the Java 8 way. Pretty nice. Notice, not stream, it's a parallel stream. That's all you have to do. JVM or the class libraries take care of the rest of it for you. So this is a really good motivation for using the streaming interface. Even if you don't believe any of the other advantages of using the functional style programming, you've got to believe that this is a better way to write parallel code. So, what are the benefits of streams and lambdas, if I haven't already persuaded you? Using lambdas results in code that is simpler to read, it's simpler to reason about, and it's far, far simpler to parallelize. Parallelism is critical. Moore's law continues to march forward, but it got turned on its side a few years ago. Chips aren't getting any faster. They're just getting wider. We're getting more and more cores on the same chip that are actually running a little bit slower than they used to. So the only way that we can make our programs faster is to parallelize them. And this finally makes it easier to do that. Still not easy, but easier. But why wouldn't we do it? There are costs. Changing all of our code takes a lot of time and effort. There are a lot of for loops in Java programs out there. There's also risk of error. There are subtle problems that you can introduce when you do this. If you're not careful, you might change the semantics of your program in subtle ways. Or you might end up calling the wrong function. You may also just end up getting frustrated because you don't understand all the rules related to scoping. But what if a tool did it for you? Then the cost is zero, the risk of error is zero, and you still get all the benefits. So, what does this paper do? I'm quoting from, or paraphrasing from the paper here. They designed and implemented a tool that automatically transforms Java programs to, first of all, convert anonymous inner classes to Lambda expressions, and to convert for loops that iterate over collections to functional operations that use Lambda expressions. So, converting anonymous classes. This is actually the really easy one. And you can see the benefit here. It's just clarity. This doesn't give us the parallelism benefits or anything, but this is the old way of doing it. We tell the thread that we want to create it with a runnable. I have to tell it it's a runnable. And, well, there's only one method in run, but I have to tell it that I'm implementing run, and I override it, and I just want to print something out. In Java 8, we can use a Lambda. The compiler looks at it and says, well, there's only one functional interface that you can use to construct a thread, so I'm going to guess that's a runnable. And there's only one method in run that you can override, so that's probably run that you're implementing. And you could just express that as a Lambda. It also does type inferencing of the variables, again, from the arguments to that method. So this is a easy simplification of the code. It reduces the lines of code that you have to sift through to find the important things. It's a straightforward transformation. This one's pretty easy to do. I actually kind of get the feeling that if you're going to do the Lambda refactoring, you might as well do this one, so they threw it in. It handles a bunch of special cases that will be annoying to do by hand. The scoping rules for Lambdas are slightly different than inner classes. It has to be a particular type of interface, so there are a handful of interfaces that you might think you could use as Lambdas, but you can't because they actually implement two methods, not just one. You can't refer to this or super. You can't use recursion. I'm not sure I've ever seen anybody use recursion in an anonymous inner class, but it is legal. Not in Lambdas though. And it figures out the syntax you need for the type inferencing. Lambdas you don't always have to put in the types, but sometimes you do. And the tool is able to figure out whether you do or not. So that's the easy one. This is the really juicy one, and the one that's exciting. Converting for loops into streams of functional operations. The tool is able to take free-form for loops, and using a conservative heuristic, it can convert many of them into chains of stream operations. Now, it's heuristic, so there are some that it can't figure out, and there are also some for operations that simply cannot be converted without completely changing the code. But it turns out that they can actually transform a huge percentage of them surprisingly effectively. So here's an example of a transformation that they make. This is actually transformed using their tool in NetBeans. Their tool is now part of the official NetBeans release. So Up here is my original example. I'm summing up all of the positive numbers in a list of doubles. The tool detects that I'm filtering out, I'm filtering to only get the positive ones. And then it sees the plus equals and figures that looks a lot like a reduction. So it converts it to a reduce operation. The code is now more explicit and trivially parallelized. So, like I said, they're able to convert for loops into chains of composable streaming operations. They support the most common streaming operations. That's the map, filter, and reduce that you're probably used to if you've dealt with functional languages. And my paper is stuck here. Sorry about that. And they also handle any match and none match, which are just predicate operations to test what's in the set. Yep.
Do these have to go inside the filter map, etc.? Like, can we assign them to a runnable A? Runnable A equals to lambda, and then
Oh yeah, absolutely.
can we name them?
Yes, if you wish to. Although in that case, I believe you need to provide some extra type information because the type inferencing won't work there. But the syntax does allow you to do that. So the question was, can you use lambdas outside of the context that I'm describing here? And the answer is yes, with a little bit more syntax because there's not enough information for the types. Okay, so converting for loops. How do they do this? So the first thing they have to do is filter out some of the for loops that they absolutely can't deal with. If your for loop has a break, they give up on it, because that's essentially a go-to, and it's really hard to convert to a functional style. I've actually thought about this a bit, and I think that there are some special cases where a break could be converted, but they're not handling that right now. They don't do anything if you have, they also ignore it if you have a return, except for the special case of returning true or false. They're able to handle that. So I said they can't handle breaks, but they can handle continues. They point out that continue is actually just an inverted if. So they rewrite the continues to be ifs and then continue on with the transformation. So once the continues are ifs, they look for all the ifs in the block. The ifs get turned into filters, and every other expression gets converted into a map. Now you can't quite do that, but it's a good place to start. Next they go through and look for maps that actually have interdependencies, that they can't just pass through to each other. And they merge those ones back together to make larger maps. So they optimistically start off and divide it up as much as they can, and then start putting it back together. And once they've converted it to all these filters and the minimum number of correct maps, they have to look at what the terminal operation is. So one of the differences between the streaming interface and a for loop is that the streaming library allows you to have lazy strings. When you do a filter, that filter isn't actually applied until somebody looks at it. For loops, on the other hand, are imperative and happen right now. So they have to make sure that the terminal operation in the chain is an eager operation, so that it collapses the result. So that can be a for each, if it has, say, a mutating operation at the end, or it can be a reduce, or it can be one of the any or the any match or none match. So as I mentioned, they use the most fine-grained operations that they can. They believe that this gives the programmer the most control over parallelism should you decide to parallelize it. It's also the most explicit. Having more steps, more small steps, seems clearer to me. As I mentioned, the last stop in the chain must be eager. And I'm just going to repeat, they do not automatically parallelize it. But what they leave you with is something that you can parallelize by adding one word, after you've looked at the code and made sure that it's actually safe to parallelize it, which is a far more complicated problem than the complicated problem they're solving. Does it actually work? Well, they tested it on 9 open source projects consisting of over 1 million lines of code with 4,300 tests. Their refactorings actually found 2,700 opportunities in that code. They ran all their tests and there were no failures. So that's a pretty good level of confidence that this is correct. But how well does it work? So this is something I really love about the way that they did this. This is a problem that they're trying to, in this problem, they're trying to do something that a human does, but they're trying to make a computer do it. The best way to test that is to compare it to humans. I love that they're comparing this to humans. I think that's something we should do more of in computer science. This is great. If we want computers to do human tasks, we need to compare them to humans. So how do they measure? And humans try to do the same task, and then they compare it to what the computer did. And they used 2 measures that they borrowed from the field of information retrieval. So these were metrics I hadn't heard before, but it's pretty neat. I think this is a clever way to do it. So the metrics they used are called precision and recall. Precision is the measure of quality. It says how well is the task or the recognition being performed. In this case, it's a task. Recall is a measure of quantity. It says, did it do it in the right places? Did it find all the opportunities? So, in addition to these metrics, they also did some quantitative metrics. They measured lines of code, which I think is actually a pretty coarse metric and easy to manipulate. And if their transformation converts all my for loops into one long line, they'll be able to prove that they produce fewer lines of code, but so what, at the expense of huge lines. But they also measured the change in the size of the abstract syntax tree. That's a lot harder to fake and is a much more sensible measure of complexity. If the tree has fewer nodes, it's easier for me to parse in my head and easier for me to understand as a programmer. Oh, what were the results? They found precision and recall for the first refactoring, the anonymous inner classes, was 100%. They found every single opportunity that a human did, and they did it just as well as a human would. For the second refactoring, the for loops, which is the harder one, they got about 90% of the opportunities that a human would. And again, 90% precision, yes, 90% recall and 90% precision, which means that in 90% of the cases, they broke it down into the same number of fine steps that a human would have. The human only found a more detailed way to break it down in 10% of the cases. So that's pretty good. The other really interesting thing they found was that there was very little clustering. This is that there were only 2.3 loops and 2.5 anonymous inner classes changed per file. The changes were really spread out. So doing this by hand would be particularly tedious. You have to look at nearly every file in your project. And this is not something you can do with a search and replace. It requires deep knowledge of the syntax of the program and an understanding of the language. You cannot express that in a regular expression. Additionally, both the lines of code measure and the syntax tree measure showed that the resulting program was simple. And that's a really good thing. So they mentioned in the paper a couple of opportunities that they missed to do a better job. And I've been thinking about this, and I think there's actually more. I think that with a bit of extra work, this could be hugely improved to do far better than the 46% of loops that they were able to convert. I think we could actually do much more than that. For one thing, they didn't handle cases where the for loop was iterating over an array. They only handled cases where it was a collection. Now, I suspect, in fact, I sent an email to the author, and he doesn't quite remember why that was. But I suspect that the Java 8 spec was in flux when they were doing this work. And the options for iterating over arrays changed several times while Java 8 was under development. So they didn't think they could do it. But it turns out that there are APIs for streaming over arrays in the final spec. 41% of the cases that they couldn't convert were because there was an array in the for loop. If they could handle arrays, there'd be a huge number of additional opportunities. I think they could also handle returns of more than just Booleans. A common pattern I've seen is to iterate over a collection and return the first element that matches a particular criteria. You can do that with filter and find first. They could also convert nested for loops to use flat map, which would expose even more opportunities for parallelism. There's certain times when reduce is actually just a count, because you're counting how many things match a criteria. So you can do that with filter and reduce, but you can also just do it with filter and count. So I think that they made a great start, and I think that it's possible to go even further and do even better. So one of the lessons that I want us to take away from this paper, I think there are 3 major lessons, and these lessons are what I love about this paper. Refactorings help us manage technical debt. Our old code, particularly if it's part of an active project that's still being developed, should be held to the same quality standards as our new code and should conform to current best practices. Refactorings like that are error-prone and tedious, but with some thought, we can teach computers to do these. And you know what? It might be a bit more work to teach the computer to do it, but I think programming computers is a lot more fun than doing repetitive tasks on computers. I'd far rather teach the computer to do my tedious task than do it myself. The final lesson, and I'm going to reiterate this, is that researchers are duplicating a human task with a computer. The best way to evaluate that is to test against humans. And I love to see computer scientists testing against humans, other than in the realm of human-computer interaction, where we're good at that. I think that we can borrow a lesson from psychology professors who use their students as test subjects. There are lots and lots of computer science students. They make great test subjects for this kind of thing. So, I'm going to open the floor to discussion, but before I do, I want to ask a question of the audience. So, first an admission. I actually love IDEs. I do most of my work in the webs. I can use Emacs. I can use VI well enough to save a file and exit. Or even better, exit without saving the current file. That took a while to learn. Escape colon Q bang. More useful than that. So, I love IDEs. I love that Eclipse knows all about the structure of my program and how things interact, and it lets me do these complicated refactorings. But I also want to automate refactorings. I want to take them out of the IDE and bring them to the command line. So what is the setting of refactoring? How do I automate these things? What tools do people use? I've written some of my own using the Eclipse AST, which is very powerful, but it's just the bare bones framework that you need to do this. It lets you manipulate a syntax tree, which is great, but there's nothing else on top of that. If you want to organize imports, you have to write that all yourself. I've seen a project called Modisco. I haven't tried it. It looks like it's headed in this area. There's another project from Google called Refaster that does a very specialized form of pattern-based refactoring. Looks like a great tool, but very specialized. So I want your advice. If somebody can tell me what they use, I want to know it. So, yeah.
So, are you familiar with, also I mostly write C++ these days.
Yep.
Clang MapReduce and Clang Tidy are amazing. Clang MapReduce it will run across an entire code base as a MapReduce and gives you full access to the AST of any C family language, so Objective-C, C, C++. And you can do AST transformations, and it will re-emit the code using Clang format as very clean, whatever C family language code. And so you can do distributed refactorings using that. And Clang Tidy is a framework for specifically doing this type of refactoring for common cases like the ones in this presentation, where you know the origin format and you know the target format, and you know that programmers probably do it a lot, so you want it to run across any type of submission into your repository, and you can just write a Clang Tidy rule and run it against any C family language that runs in your code.
That actually sounds kind of similar to what I'm doing with the Eclipse AST. It gives you the same ability to manipulate Java files. But I think what I'm looking for is something a bit richer. Like inside Eclipse itself, if you're writing refactorings in the IDE, you can make these changes and you can add imports and it'll automatically organize the imports for you. But these tools are, those tools, the things that are built on top of the AST are all tied to the IDE. And I want to run them outside of the IDE. But yeah, having the transformation framework like Clang is fantastic, and I will definitely take a look at that for manipulating C code, which I also have.
I've seen this strange tool called DXL. Have you heard of that one?
You know, I'm going to get a pen out and start writing this down. Okay, so we've got Clang, DXL.
DXL is a Canadian group.
I do have fondness for Canadians.
I'm saying they use a very strange language to build the system. It's a translator of language to language.
Okay, I'll take a look at that. Yeah.
Have you compared the Eclipse interfaces to IntelliJ's?
I have not. So I admit a bias here. I used to be at IBM Canada, and Eclipse came out of the lab where I worked.
Your bias is wrong. IntelliJ's about 1,000 times better.
But can I use it in batch mode?
Yeah, their APIs are available for batch stuff, I believe. Their plugin architecture has like a headless mode.
Okay, I know some people have built headless modes for Eclipse, but it's a total hack.
No, that's IntelliJ's correct architecture. I'm just kidding. Seriously, IntelliJ's really good.
I've heard a lot of good things about it. I'm biased. Yeah.
I'm going to back it up. Refactoring, there's a great community of who make plugins for IntelliJ for every language, C++, you name it, Java, everything. Cross-platform, it's beautiful. The shortcuts are amazing. There's a lot of plugins for refactoring. There's Vim plugins. If you make something that tries to do automated refactoring, it will be huge. There's already plugins that automatically imports for you. It's typing classes. So I feel like there's some kind of automated thing that would be an easier step possibly in IntelliJ, just because it's also open source and whatever. Because they already have it tested in place. It might be not a crazy addition.
So the biggest thing that Eclipse is missing is Eclipse does Java analysis ad hoc. They basically are just writing their own AST walker. Whereas IntelliJ has a full framework for attribute grammars, so you can write Java code that can do lazy and incremental computation of analysis on ASTs for live analysis. So Eclipse does that all ad hoc, and like IntelliJ actually has like tools for helping optimize that sort of analysis, correct it, validate it, etc.
Oh, yeah, that sounds really promising. So you don't have to answer my question. General discussion. Yeah.
So I presume arrays are hard because you're in control of how you get into the array, and you would have to analyze the body of the loop to make sure that you don't mess with the loop variable. Because as soon as you start doing that, it's no longer a linear transformation of the loop.
Right, so you can, so the question is about whether or not dealing with arrays, and because you can access arrays arbitrarily. That's true, but in Java 5 they introduced the enhanced for loop, which you can use to iterate over an array in order. And you actually don't even get the index when you use that, that method. So you can't even write back into the array, or at least not easily.
Oh, I see. So they can't even do arrays with the enhanced for. I mean, I can see why an arbitrary for loop.
Oh yeah, the arbitrary 3-clause for loop they
No.
completely ignore. But in fact, they have another tool that they wrote earlier that converts classic for loops to enhanced for loops. So there's, I think they felt there was no point in duplicating that in this work. But yeah, I agree that you can do arbitrarily complicated things with arrays, but you can also do really simple things.
Well, presumably that other tool that you just mentioned, then they would have to analyze the loop body to make doubly sure that they're not.
Exactly.
Okay.
Yeah, so they already know how to make that transformation.
Okay.
Yeah, David.
So speaking of arbitrary, complicated, horrible arrays, there is a framework that is designed to identify how to simplify that into kind of non-intersecting nested for loops called GIMPL, and that does loop dependency. It does loop iteration dependency tracking and so it can track like multiple nested arrays and figure out how like if it sort of it does a basis vector transform on your nested loops. But anyway, I don't know. You could solve the nested complicated array manipulation problem with that.
And I think as long as you're not actually mutating the array while you're iterating over it, it should be fairly straightforward.
GIMPL actually handles the mutating the array case too.
Right. But I think once you throw mutation into the mix, you can't really rely on the streams interface anyway, particularly if you're going to parallelize it.
Right.
Yeah.
So did they do any analysis of the impact on like the garbage collector or the runtime? Because it seems like they're allocating a lot more objects and they're doing a lot more iteration of this.
Yeah, that's a good point. So the streams interface definitely does allocate more objects, but they're very short-lived objects. They're short-lived in the sense they only live for the duration of that function, and they never escape the function. So assuming that JIT is doing its job properly, it should be able, that's a huge assumption here. It should be able to detect that these things don't escape and simply stack allocate them or even decompose them. Whether or not it actually does that in every case is really hard to say. But small short-lived objects are generally not expensive. They only live in the nursery. They get collected, so even if they do escape from the stack, they rarely make it past the nursery and don't have a long-term, an impact on the long-lived part of the heap. If your application is really that sensitive to garbage collection, especially local garbage collections, you should be considering a real-time garbage collector, or not using a garbage collected language. This coming from a guy who wrote garbage collectors. So. Yeah.
So you were saying that using the streams framework, you want to kind of break things up into fine-grained steps. There seemed to be some tension between this tool sort of breaks it up as much as possible, then starts to collapse them. But you were giving the intuition that for parallelism, you don't want to collapse it too much. So presumably there's some heuristic at which they decide this is the right balance, or?
So my understanding of what they're doing is they break it up as much, they break it up in fact more than possible. So they break up every single operation into a separate step. And then they detect which operations actually had to be together because they're interdependent.
Okay.
So it's not a heuristic so much as a hard rule. They break it up as much as possible, but no more.
Oh, so they overshoot. to the
Yeah,
point that
exactly,
it's
they
wrong,
overshoot and
then
then they reconsolidate where they have to.
So maybe I'm lacking intuition for why you want to break it up as much as possible, why would that necessarily be better for the parallelism?
I have to admit that I'm kind of taking the authors on their word on this one.
I think it just gives you more places to insert, parallelize the next operation.
It breaks it down into more pieces, which isn't necessarily optimal because there's a granularity issue. If the pieces are too small, the overhead of the concurrency might dominate. So it's not, I think it's confusing topic, but I think you're right, that's basically
I think it's basically
opportunities.
Yeah, I think they basically did it so that like you can like do line copying to insert parallel operations.
And the way I showed doing parallel is kind of a shortcut. You can replace stream with parallel stream, but the other way to do it is actually to insert a call to parallel somewhere in the chain. And I'm not quite sure what the consequences are, depending on where you choose to insert it.
I think that's just what it is. Like it's just more periods means more places to put in the word parallel.
Presumably there's a synchronization step at every time you do one of these stream operations. You have to finish the
Yeah,
parallel.
so you find a period and then you indent a bunch of rows, like 3 or 4 lines or whatever. Like if you have like map, you have like map A through F. You like, I want to parallelize map D, C and D. So you indent C and D, you wrap them in parentheses, and you stick the word parallel and put that in parentheses, something along those lines.
But I think it's wrong to think of a synchronization point between steps, because the map isn't complete. We don't complete each stage in the chain before we start the next one.
Oh.
We run it for each element. Because it's streaming, so it's kind of a lazy evaluation. When you ask for the first element, we apply the map, then the filter, then the reduce, then we go to the second element and do a map, filter, reduce. We don't do all the maps and store the results. We never store the intermediate results. Did you have a question?
That was the garbage collection.
Okay.
Yeah. Your very early slide, it was a really minor nitpick, but it was the reduce. I was kind of surprised they didn't inline the 0, that it was starting off with this double and then return that. And it seems kind of strange that they didn't do that.
I agree. I think it's just a. I think that the tool could be further improved. I absolutely agree. It should have put the 0 right into the call. And something I didn't show there, I fudged a little bit. They actually inserted an unnecessary map step into that example as well that I removed for the sake of the example. They did a map of V to V. I'm a little bit suspicious that what ended up in NetBeans isn't actually quite what they'd implemented, because it seems to be slightly worse than they described. It's still really good. It's just not quite as good as they described.
The continue turning into ifs, you can use continue with a label, right? So you can jump out of it.
That's correct, yeah. That is an exclusionary criteria.
Okay.
If you use a continue with a label, that's essentially a go-to.
This is not a question about refactoring, it's a question about the streaming framework. Is there an equivalent of like closures reduced, which lets you do early termination of stream operations?
I'm not sufficiently familiar with either.
It's just the idea that you do a reduce and then you wrap a return value from reduce in a distinguished type. So like you said, like instead of I have integer, 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 and then reduced integer, and then it just breaks out of the.
Yeah, I'm insufficiently familiar with either either closure or the streams interface to say for sure.
The cheat button.
Yeah,
Yeah, it's a dynamic trick, yeah. But I just didn't know if there was like a side effectual cancel or abort or something.
Not that I'm aware of.
Couldn't you implement that with stream?
Well, what's
filter?
Yeah.
Couldn't you implement that with filter?
It's an escape hatch, right? You wrap the type and you say there's the special flag of things that you should immediately get rid of and jump out of.
It's one of those things that was like really upsetting the Haskell guys on like the whole transducer thing.
What's the application?
Any early termination, so like find first sort of situations. So, but other ones are like.
But they don't reduce. But
so it's not just find. Yeah, it's like while you're reducing, you like decide you're done.
sure.
Because the problem is that, well, sort of. The thing is that find first is find first is insufficient because that means you have to do the filtered, and so if you have a reduce somewhere in your operation chain, reduce is eager.
Right,
And
right.
so to abort an eager mapping or an eager filtering.
Yeah, I guess I can imagine a case, say if you're reducing to doubles, if you eventually reduce to nan, there may be no point in continuing any further.
I think the canonical example is take a while, or take a while.
Right, yeah. I don't know how you would parallelize that. So that might be one reason that they wouldn't do that.
So Clojure actually does parallelize it as well, because you can have multiple instances combined.
Okay.
Yeah.
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 I don't know. It's their first cut at doing streams, so maybe Java 9. Yeah.
So after you make these transformations, does the code become completely incompatible with previous Java versions? That is, for example, the first transformation might be equivalent to anonymous classes, so will it work there?
Right. So the question is, when you make these changes, does it become incompatible with previous versions of Java? So I'm going to address the two different transformations separately. The first is the anonymous inner classes. And the answer to that is yes and no. Your source code is now Java 8 specific. However, the bytecode should be unchanged. So it will remain compatible with older versions of Java. With the for loop transformation, the answer is it is incompatible, completely incompatible with previous versions of Java because the streams library is not part of the standard Java libraries in Java 7. So you will be using classes that don't exist.
And is there a way to backport those? Or?
There have been various different ways over the years to backport features from newer versions of Java to older versions. I'm not aware if anyone has done that. It seems unlikely in this case because you need to use a Java 8 compiler and some backwards compatible class libraries. I haven't seen anything like that, but it's not impossible.
Anybody else? Any more questions?
Yeah.
Why would anyone want to run Java on Palm
So, that's an excellent question.
No, it's not. It started out as a set-top box language.
Yeah, so Java actually was an embedded language to begin with. It came out of Oak. And we got it running relatively quickly on Palm, and we provided a direct access to all the Palm APIs. So we had a native library that you could invoke, that you could call the APIs. And as long as you weren't doing any deep number crunching or something, most of your time was spent in the libraries anyway. And you got the advantage of being able to use the Java libraries, which was pretty nice because if you ever did any Palm OS development, it was pretty primitive. But we didn't have a JIT, not at 68K. We had a really tiny garbage collector. The garbage collector, I think, was about 15 kilobytes of code. Which in the old days would have been huge, but we were pretty proud to get it down to that. And we were actually the official JVM for Palm Pilot and shipped in the last few years before they went under. So if you had a Palm Pilot, I guess a model, it was after the 5C, but when we were on 68K and the ARM versions for a couple models. So if you owned one, you may have had my VM on your Palm Pilot.
So I'm only 28, so frame of reference. What years are we talking about here?
This would be around 2003.
Okay.
That?
So like the beginning of the iPods.
No. Predates iPods, so maybe I. When did that?
iPod in like 2001.
What's that? 2001 iPod already?
Yeah.
Wow.
Yeah, I remember.
Oh, it's getting a hard
like
drive.
2 songs on it. But
Yeah, so maybe you're wrong. Maybe it would have been.
Creative known methods.
What's that?
Oh, you use which search engine you're using at that time? Google probably become popular in 2000, right? So if at the project you're using something like Lycos, then it's not actually 2000.
I remember using Alta Vista when I started. And I remember it was going downhill when I searched for DEC Alpha Assembly, and the top 5 hits were all pornography.
You were searching for deck that tells you what the time period was, right?
Well, that was before Palm Pilot. That's when I was doing DEC Alpha stuff. Thank you very much, everybody.